Assalamu alaikum students. Today we are going to discuss about sludge treatment and another very brief topic, on-site sanitation. Let's first define the sludge or residual solids. It is the end product of wastewater treatment, whether it is biological or physical or chemical treatment. So as we have discussed earlier, that the purpose of primary sedimentation tank is to remove the suspended solids present in raw wastewater, which are mixture of organic as well as inorganic. Mostly they are organic. Similarly, in the secondary sedimentation tank, the solids which are produced in the aeration tank or trickling filter or aerated lagoon, means any secondary biological treatment process produces the solids in the form of biomass. They are removed in secondary sedimentation tank. So both of these sedimentation tanks produce large amounts of suspended solids which contain a lot of moisture inside. Therefore, the terminology used is sludge. Now, sludge from municipal treatment plants is likely to contain microorganisms which may contribute to transmission of disease, as well as organic and inorganic contaminants which may be toxic to humans or have the severe effects on environment in general. For these reasons, proper handling and management of this material, this sludge, is very important component of the design and operation of a wastewater treatment plant. Another very interesting fact about sludge handling is that it accounts for at least 30 to 40% of the capital costs of treatment plants, 50% of the operating costs, and around 90% of the operating problems are related to sludge handling and sludge treatment. So the key objectives of the sludge treatment includes firstly the reduction of the moisture content of the sludge, thereby reducing the sludge volume. So principal objective is basically reducing the volume of the sludge, and that is achieved by reducing the moisture content of the sludge. The reduction in moisture content of around 1-2% can lead to significant reduction in the sludge volume. Removal of pathogens is another objective. Recovery of methane: in case of anaerobic sludge treatment, methane can be generated and recovered as a renewable energy source. And the final objective is, if we want to use the treated sludge as fertilizer or soil conditioner, we obviously have to treat it first, then it may be used as fertilizer. Sewage sludge generally consists of the organic and inorganic solids present in raw wastewater and removed in the primary clarifier, plus the organic solids or biomass which is generated in the secondary treatment and removed in secondary clarifier. The inorganic fraction of the sludge may be assumed to have a specific gravity of about 2.5, while the organic matter has a specific gravity of 1.01 to 1.06 depending upon its source and its characteristics. The domestic wastewater typically contains 100 to 350 milligrams per liter of suspended solids depending upon the flow. Communities which contain major industries may vary from this value. These typical values are for domestic wastewater only. Out of this quantity or concentration of solids in raw wastewater, approximately 60% may be expected to be removed in primary clarification. The remaining portion of suspended solids goes to the secondary treatment, where it is either oxidized in biological treatment or it is converted into biological mass. The biological solids generated in secondary treatment may be 0.4 to 0.5 kilograms per kilograms of BOD applied in attached growth processes like trickling filter, whereas 0.2 to 1 kilograms per kilograms of BOD applied in the suspended growth processes. These are the typical quantities of solids in the form of biomass that is expected to be generated in secondary treatment. What happens in secondary treatment? The bacteria oxidize the dissolved portion of organic matter and convert it into stable end products, oxidized products like carbon dioxide, and major portion goes to the biomass itself. So that biomass growth or production is in this range for attached growth processes and in this range for suspended growth processes like aerated lagoons and activated sludge processes. So let's solve an example problem to illustrate how to calculate the amount of solids or amount of sludge produced from a primary or secondary clarifier. So the problem states that you have to estimate the solids production, it means dry solids, from a trickling filter plant treating a flow of 1000 cubic meters per day with BOD of 210 milligrams per liter and suspended solids concentration of 260 milligrams per liter. Assume the primary clarifier removes 60% of suspended solids. This is a typical removal of primary clarifier, and it also removes 30% of the BOD, which obviously would be in the form of suspended organic matter. So in this 60% removal of suspended solids, this BOD removal is also included. However, BOD removal is required to estimate what percentage of organic matter went to the secondary clarifier and what was the amount of solids produced in secondary treatment and removed in secondary clarifier. So let's solve this problem. For solution, first we have to estimate what the primary clarifier will produce as solids. So as we have discussed earlier and given in the problem statement as well, that 60% of the suspended solids will be removed in primary clarifier. So the total amount of solids produced can be estimated by multiplying 0.6 60% with suspended solid concentration of wastewater, which is 260 milligrams per liter, and the total amount of discharge or flow, which is 1000 cubic meters per day. So this is a typical calculation of loading, mass loading of any contaminant, such as we have been doing this for calculating the mass load of BOD in various problems. So discharge multiplied by concentration multiplied by the fraction of the solids which have been removed in primary clarifier. So the answer is 156 into 10 is for 3 grams per day, or simply 156 kilograms per day. Now secondary clarifier will remove the suspended solids which are in the form of biomass, and that biomass is produced in the secondary treatment processes based on suspended and attached growth processes. It has different value of production, but the production is linked with the load of BOD applied to secondary treatment, which was shown to you in the previous slides, that let's say approximately 0.5 kilograms of biomass or solids will be produced per kilogram of BOD load into the secondary treatment. Therefore, first we need to estimate what BOD load in kilograms is going into the secondary treatment units. So secondary treatment will receive a BOD load of 0.7, means 70% of the original BOD concentration, because 30% will be removed in primary clarifier. So 70% goes to secondary treatment. 0.7 of 210 multiplied by discharge gives the value of 170 kilograms of BOD per day. Now taking a typical value for attached growth processes from the range given on the previous slides, 0.5 kilograms per kilograms of BOD is taken here. This is the amount of solids which will be produced as a result of BOD consumption, and the solids are the biomass here. So So 0.5 multiplied by 147 will give you 74 kilograms of suspended solids or solids will be produced from the secondary treatment, and they will be removed in the secondary clarifier. So mass of the dry solids total which will be generated or produced from primary and secondary clarifiers will be 156 produced in primary clarifier plus 74 produced in secondary clarifier. So a total of 230 kilograms per day of dry solids. Now this dry solid would have a moisture content of uh, let's say 95-96% or 98%. So depending upon the moisture content, you can estimate the total mass of the sludge as well as the volume of the sludge using the specific gravity. So typical solid contents in the primary sludge are in the range of 4 to 6%, whereas its moisture content is 94 to 96%. Waste activated sludge contains a lot of moisture content, 98.5 to 99.5, whereas trickling filter is comparable to the primary sludge, which contains 95 to 96% of the moisture content, and the rest are solids as 4 to 5%. In the raw wastewater, around 0.1%, in raw domestic wastewater particularly, 0.1% are solids and 99.9% is the moisture or water. In the sludge, you can see in the primary and trickling filter sludge, the moisture content is slightly reduced and solid contents are enhanced, whereas in waste activated sludge, this moisture content is still very high, very close to the raw wastewater. Due to this enormous moisture content available or present in the sludge, the quantities of the sludge in terms of volumes are very high. Therefore, the treatment processes for sludge are focusing or mostly targeting the moisture content reduction from the sludge. The effect of moisture content on the sludge volume is enormous, and sludge handling techniques are directed towards reducing the moisture content and thereby reducing the volume of the sludge. As I have mentioned on the previous slide that most of the sludge handling techniques are directed towards reducing the moisture content and ultimately to reduce the volume of the sludge. So a typical flow sheet for biological sludge treatment includes the first unit of sludge thickening. The purpose is to thicken the sludge to reduce the moisture content by gravity settling. Then comes the sludge digestion, which can be aerobic or anaerobic. This is similar to aerobic and anaerobic digestion or oxidation of organic matter in the secondary treatment. And here the organic matter is in the form of sludge. The third unit is the dewatering, and again the purpose of dewatering is to reduce the moisture content. After dewatering, dry mass of solids are left, which is disposed of. Now supernatant of this digestion unit and underflow of the dewatering unit means the water which is separated from the sludge in both of these units goes to primary sedimentation tank. It is redirected back to the start of the wastewater treatment plant. So here is another example problem just to illustrate how the percentage moisture content affects the sludge volume. The wastewater treatment plant produces 1000 kg of dry solids per day at a moisture content of 95%. The solids are 70% volatile. Volatile means organic with specific gravity of 1.05, and 30% are non-volatile means inorganic with a specific gravity of 2.5. We have to determine the sludge volume as produced. and after an anaerobic digestion process, which reduces two things. First, it reduces the volatile solids by the digestion, oxidation by 50% of the original amount, and it produces a sludge with moisture content of 95%. So it has also reduced moisture content by a value of 5%. Originally it was 95%, after digestion it is 90%. So you have to estimate the sludge volume as produced and after the digestion process. So in this situation, let's first deal with part A. We should determine the volume of the sludge as produced. So the original mass of the sludge would be mass of the dry solids divided by fraction of the solids. Since the moisture content is 95%, the fraction of solids would be 0.05. So dividing, we get 20,000 kilograms per day. This is the mass of sludge. Originally in the statement, mass of dry solids was provided as 1000 kilograms. We divided it with fraction of solids. So hence we get the mass of total sludge, which is 20,000 kilograms per day. Now as in the statement, 1000 kilogram is dry solid weight, of which 70% is volatile and 30% is non-volatile. Hence the sludge contains volatile solids, non-volatile solids and water as moisture. So first let's determine the volume of the volatile solids and then non-volatile solids and then water, and later we will sum up these to calculate the total volume of sludge. So for volatile solids, the mass is 70% of the total 1000 dry solids, so it is 700 kilograms. To get the volume, we can divide it with the specific gravity. So 700 divided by 1.05 gives 667 liters. Non-volatile solids are 300 because they are 30% of the 1000. So 300 kilogram divided by their respective specific gravity of 2.5, it gives the volume of 120 liters. Now what is the water? If 20,000 is the total mass of sludge and 1000 is the dry solids, the mass of water would be 19,000 kilograms. And volume of water would be same, taking the specific gravity as 1. So the total volume of the sludge would be 19,787 liters. Now after digestion, which is part 2 of the problem, it was stated that volatile solids are reduced to 50% of the original. So originally they were 700 kilograms. So after 50% reduction, they are left as 350 kilograms. And moisture content has been reduced to 90%. Therefore, the dry mass will be reduced to 650 kilograms because non-volatile solids, which were 300, remain same. Whereas volatile solids, which were 700, now they have been reduced to 350. So 350 plus 300, the total dry mass would be 650 kilograms. And the sludge mass, using this moisture content and the solids fraction of 0.1, dry mass of solids divided by fraction of solids gives us the total mass of the sludge as 6500 kilograms. So now you can estimate, you can imagine how much reduction in mass has been achieved as a result of digestion process. Originally it was 20,000 kilograms, now it is 6500 kilograms. And digested sludge would contain these elements, volatile solids. Originally they were 700, after digestion reduced to 350, so its volume would be 333 liters. Non-volatile solids unchanged because they are not affected by digestion. And the water, now subtracting 650 kg from 6500 gives the value of 5850 kilograms, and the volume would be the same. The total volume of the sludge would be 6303 liters. So as compared to originally the 19,887 something, now the volume has significantly reduced, and principally it has been reduced because of the moisture content, right? As you can see, the change in the volume of the volatile solid is not that significant, and non-volatile solids volume is not changed. The only significant change from 19,000 liters to 5,850 liters is in the water mass or water volume because of the change in moisture content. The first unit applied for sludge treatment is sludge thickening. The purpose of sludge thickening is to reduce the moisture contents and to increase the percentage of solids in the sludge. The thickening of the sludge is most commonly achieved by gravity thickness. The other methods used are flotation and centrifugation. The gravity thickness are most commonly used. They are just like sedimentation tanks. As you have studied the primary and secondary sedimentation tanks, this is also a sedimentation tank in which sludge is applied, and it settles down by the mechanism of type 4 settling, which was referred to as compression settling. If you recall, we discussed that in water treatment topic of sedimentation. Sludge thickening involves type 4 or compression settling in just a sedimentation tank. The thickened sludge is removed from the bottom, and the supernatant, which is separated from the sludge, the water, is removed from the top and returned back to primary sedimentation tank for further treatment. The second treatment unit employed for sludge treatment is sludge digestion. This is the process of treating the organic solids to make them stable, to oxidize them basically, to make them stable so that they are not subject to further degradation or they are not putrescible anymore. The methods employed for sludge digestion includes anaerobic digestion, aerobic digestion. Both of these are biological processes. The other methods include alkaline stabilization, composting, or incineration. Out of these methods, anaerobic digestion is commonly used because of its advantages such as no requirement of oxygen in comparison to aerobic process, and the other advantage is the production of methane as byproduct of digestion. This figure represents the overall anaerobic digestion process. So in the first stage of the process, complex organic compounds such as carbohydrates, proteins, lipids are broken down with the help of enzymes into soluble organic or simpler organic products such as glucose, amino acids, fatty acids, etc. This process is known as hydrolysis. Then acid forming bacteria, which are also known as acid producers, convert these soluble organic products to organic acids such as acetic acid, propionic acid, etc. These organic acids are further converted by methane forming bacteria, which are also known as methanogens, into methane and carbon dioxide, and further cells, obviously biomass, new bacterial cells, and stabilize organics. This overall process, particularly the last one, which is methane forming bacteria, which converts the organic acids into the methane, works best in the pH range of 6 to 8. And to adjust the pH, lime is added if required. Modern digesters are two-stage high-rate processes. In the first stage, heating and mixing is provided, whereas the second stage is quiescent and works as thickener or a settling unit, in which different layers are then formed. At the bottom, this is digestive sludge, this is supernatant layer, and then the scum layer, and finally the gas storage above it. Similarly here in the first stage, since the reaction starts, so gas can be produced, so gas storage is provided at the top of this sludge. Now why the sludge is heated in the first unit? Because the temperature has a significant effect on this anaerobic digestion reaction, and it can significantly reduce the required retention times and hence the volume of the digester. For example, at 20 degrees Celsius, if 10 days are required, 10 days of retention time, for 35 degrees Celsius, only 2 days would be required. So this much is the significance of the temperature. Therefore, in modern anaerobic digesters, they are both heated and mixed, and the temperature is normally maintained at close to 35 degrees Celsius, and mixing is sufficient to completely intermix the contents once daily. The gases produced in anaerobic digestion consists of 60 to 70% methane by volume, and the remaining being the carbon dioxide and traces of ammonia, nitrogen, hydrogen sulfide, etc. Because of the contaminants, particularly carbon dioxide and H2S hydrogen sulfide, methane is not a very good fuel. This mixture of gases is not a very good fuel because carbon dioxide is not combustible and hydrogen sulfide produces sulfuric acid when it is burned. Therefore, these two gases have to be stripped off, have to be removed from the gas, separated from the methane before it can be used as a fuel gas. The next treatment unit is sludge dewatering. Dewatering processes may be usefully divided into air drying and mechanical methods. Air drying includes those methods in which moisture is removed by evaporation and gravity or induced drainage, such as in the case of sand beds or sludge drying beds. Whereas in mechanical methods such as belt filters, mechanical techniques are used to separate water from the solids. Let's first talk about sludge drying beds or sand beds. Sand beds are the oldest sludge dewatering technique and consists of around 100 to 300 millimeter layer of coarse sand underlain by layers of graded gravel, which is from 3 to 6 millimeter at the top and 40 millimeter at the bottom. This is the size of the gravels. The overall thickness of this gravel layer is around 300 millimeter. The bottom of the sludge drying beds is usually natural earth graded to 100 or 150 millimeter drain tile placed on 6 to 9 meter centers. Side walls and partitions between bed sections are of concrete or wooden planks and extend 300 to 400 millimeter above the sand surface. Beds are operated by filling them with digested sludge to a depth of around 200 to 300 millimeter. Dewatering occurs as a result of drainage. The water percolates down and evaporation and is very much affected by the climate. In dry climate, sludge will be dewatered easily, whereas in wet climates there would be some problem for dewatering. Therefore, covering the beds with glass or some other plastic sheets, for example, has proven to be helpful in wet climates. The beds are 6 to 10 meter wide and up to 40 meter long, and at least two beds are provided in even the smallest plants, whereas in large to medium plants multiple number of beds are required. Typical loading rates for digested sludges range from 60 to 200 kilograms of solids per square meter of the sludge drying bed area per year for the digested sludge, not for the raw sludge. After digestion, this could be the loading rate to be applied for sludge drying beds. Drying takes from a few weeks to a few months depending upon the climate and the season, and after dewatering, the sludge solids contents will range from 25 to 35% and volume will have been reduced by 80 to 85%. The dried sludge can be removed from the bed with light mechanical equipment such as front-end loaders. A small amount of sand is lost in each drying cycle and the bed must be refilled periodically. Sludge drying beds are one of the cheapest methods for dewatering of the sludge. However, they require very large land area because the dewatering and drying process is occurring naturally by air drying, by drainage and evaporation. The area required for sludge drying beds can be estimated by the loading rates given on the previous slide. So for such applications where land area availability is not up to the requirement of the sludge drying beds, where land spaces are limited, for example in industries, the mechanical dewatering processes are used there. Mechanical dewatering processes include belt filters, pressure filters, vacuum filters, centrifuges, and a number of other similar devices. Out of all these, belt filters have become the most popular sludge dewatering device in new installations because their capital cost and operating costs are generally less than other mechanical techniques. And they also produce a sludge which can be handled as a solid. These machines are made in a variety of configurations consisting of one or more endless woven belts which pass over and around a number of cylinders. So in most designs, the chemically conditioned sludge is fed to an open belt surface on which the gravity drainage occurs. As the belt moves forward, the gravity drainage would occur. At the end of the gravity drainage section, this section, provided the sludge has been properly conditioned, the solids content here should be 10% or more. At this moisture content of 90% or lesser, it behaves as solid and can be subjected to pressure, shear and vacuum in the subsequent subsections of this belt filter. A second belt is then gradually brought down towards the moving sludge at the end of this gravity zone and gradually applies pressure to the solids, squeezing out additional moisture. As the paired belt move around these rollers, their speed relative to each other varies and the sludge mass is sheared, aiding in release of the free water. The pressure gradually increases through the machine and in some designs a partial vacuum is also applied. The belts then separate at the end and the sludge cake is dislodged by scraping the belt or by passing it around a very small radius roller. So this product can be expected to have solids content in the range of 12 to around 40%, whereas 20% is the typical value of the solids content in this sludge obtained. As I mentioned on the previous slide that chemically conditioned sludge is applied on the belt filters. So why chemical conditioning is required? Because it is not easy to separate water from the solids. In natural processes such as sludge drying beds, since long retention times are provided, therefore conditioning is not required. Digested sludge can be applied directly to sludge drying beds. Whereas for mechanical dewatering processes such as belt filters, sludge has to be first chemically conditioned so that dewatering can be enhanced. So chemical additives which are used commonly for this purpose to enhance the sludge dewaterability include ferric chloride, lime, and organic polymers. The product from the belt filter, I have already mentioned that, can be expected to have solids content range from 12 to 40% with 20% being the typical value. Loading rates for the belt filters are in the units of kilograms per hour per meter of the belt width. So these loading rates and the performance of the belt filters vary depending upon the type of the sludge and the pre-treatment applied with the help of these chemicals. So next we are going to discuss a very brief topic of on-site sanitation. On-site sanitation means the sewerage facility required at construction sites where proper sewerage system is not available, and at such sites or such communities where the proper sewerage system is not installed and is not economical to install. Therefore, for each house, separate sanitation system can be used to dispose of its wastewater. So typical on-site sanitation is employed using the first a septic tank, and then effluent from the septic tank is disposed of through a soak away or soakage pit or a drain field. Let's discuss about these two units individually. So first about the septic tank. This is an underground structure, the purpose of which is collection, storage, and to some extent the treatment of sewage. So it also does partial treatment of sewage. So the septic tank is designed to accomplish two tasks. First, the clarification, that is the removal of suspended solids primarily, and then other things such as fats, oils and greases. And the treatment, which is partial decomposition or partial oxidation of the settled organic matter by anaerobic digestion. So what happens is that wastewater from a house comes to a 2-compartment or 3-compartment septic tank. The suspended solids, which are organic suspended solids of domestic wastewater, they settle down at the bottom of the first compartment, and the rest of the suspended solids which are remaining, they can also settle at this bottom of second compartment. So these settled suspended solids then undergo anaerobic decomposition by bacteria. So organic matter is oxidized into end products of typical anaerobic decomposition such as H2S gas, methane gas, carbon dioxide, etc. The lighter particles such as oil and grease particles, they accumulate at the top surface of the septic tank, and clearer water goes to the second compartment and from there to the outlet to the drain field or soakage pit. So we are discussing the septic tank as a method of wastewater disposal. So prior to disposal through a soakage pit, the wastewater is settled, is clarified and partially treated so that relatively clear water is disposed of into the soil using the soak away. However, as I mentioned while talking about the sewer system design, that septic tanks are also applied nowadays in urban areas as part of the bylaws. In every house septic tank provision is mandatory to achieve the clarification of the sewage prior to its discharge into sewage system. The objective of that is that the suspended solids which have settled here should not go to the sewage system, such as and similarly the grease and oil should not go to the sewage system. So the problems, the operational problems of the sewer system can be avoided or eliminated or reduced to some extent. The partially treated effluent of a septic tank is then further disposed of into the soil with the help of a soak away a drain field, or as it is also called as soakage pit. Soakaway is an underground soil treatment system which receives partially treated sewage from a septic tank and disposes it off into the soil. So this is effluent coming from the septic tank. It is disposed of into this soakage pit. This pit is just like a brick manhole, you can say. The walls are brick and it is rock filled around 15 centimeter thick layer, or more thickness can also be provided. This is the rock filling around and under this soakage pit. So wastewater which is partially treated would percolate into the soil through its bottom and through its sides, and will get the treatment through the soil filter. The soil, since it's a natural filter, it can remove conventional pollutants, almost all of the conventional pollutants, and to some extent the heavy metals and other pollutants as well. So two important notes for this on-site sanitation technique is that effluent from a septic tank must be discharged into a soakaway or soakage pit, and the bottom of the soakage pit must be at least 3 meters above the groundwater table to avoid the contamination of the groundwater. The 3-meter soil filter is enough to remove pathogens and other conventional pollutants. Another important thing is regarding the septic tanks, that since odorous gas is to be expected as a result of anaerobic digestion, so the outlet pipe for the gas should be provided above the human height. And the maintenance of the septic tank and the soakage pit is also a very important factor. Desludging of septic tank is conventionally required after 2 to 3 years. However, during this time of 2 to 3 years, both the septic tank and the soakage pit must be inspected carefully for any problems or any issues. So this is all for the topics included in this lecture. If you have any queries or questions, you may ask in the question answer session this week. Thank you.